Here are solutions to homework set number 2 for ECE 111. This week we're looking at MATLAB and trig functions as well as solving functions equal 0. Now the first one is rectangular to polar conversions. When you do a plot command in MATLAB, the plot command is always in Cartesian coordinates, x versus y. If you have a polar function, I need to convert polar to rectangular. And the relationship is that x is our cosine theta, y is our sine theta. So to do that, I'm going to have angle. Theta isn't on my keyboard, so I just use Q for angle. Angle goes from 0 to 1, steps of 0.01. So that gives me 101 points in that matrix, times 2 pi. So angle goes from 0 to 2 pi. Those are natural units. Angles are periodic in 2 pi in radians. R is cosine theta plus 1. Calculate x and y coordinate. I've got to use that dot notation because R is a 100 by 1 matrix. Q is a 100 by 1 matrix. So when I multiply them, I can't do a matrix multiply. The dot time tells MATLAB do an element by element multiply, then it's happy. And if you plot it, you'll get a circle. Basically, sine, cosine are all about circles. If you have r equals cosine theta, you get a circle. R equals sine theta, you get a circle. R is cosine theta plus sine theta, you get a circle. So trig's all about circles. Problem 2. If I change the function to r is the square root of theta, everything stays the same, change this one line of code, I get a spiral. And this keeps on spiraling out as you go on. If I change the function, sine 2 theta times cosine 3 theta, I get a dragonfly. So it is kind of pretty shapes. That's the first 3 problems. Now, the next 2 problems go back to homework set number 1. In homework number 1, we try to solve 2 equations, 2 unknowns. And one way to do that is to plot them. So this is y1, that's y2. This function right here is y1. This function is y2. Where they intersect are your solutions. Graphical is one way to find the solutions to 2 equations, 2 unknowns. There's another way called Newton's method. With Newton's method, what you do is you guess, say right here, and then you perturb it slightly. And really what you're doing is taking the difference in the 2. If you take the difference in the 2, I get some function like this. Actually only 2 solutions, but you get the same idea. I'm going to take a guess, perturb it slightly, and then draw a straight line. Where does that intersect the x-axis? That's my next guess. Keep iterating. That's Newton's method. In MATLAB, it looks like this. I've got my first function, second function, there's the difference. Perturb it slightly. My perturbation is 0.01. Calculate the first function, second function, find the difference. And now, if I have 2 points, there's my function. Here's the first point, x1, y1. Here's my second point, it's actually over here, x2, y2. If I draw the straight line and intersect, that guy right there is x3. That's this equation right there. My next point is the previous guess minus the slope, actually the inverse of the slope, times the error, and iterate. When I do that, I need to know the answer to find the answer. That's a problem with Newton's method. If I guess an answer close to -2, I get this answer. Guess, my initial guess is close to +1, I'll find this answer. So if I do that, here's my first guess is -2.5. These are my guesses versus time, and the error, you see very, very quickly, I converge. That's the first solution right here. That's actually -1.802028387. A few more decimal places, then I'll read off the graph. If instead I guess close to here, say make my initial guess +2, it'll iterate and find the solution close to +2. And notice with the errors, it very quickly converges. After like 4 or 5 iterations, you're there. So the second solution is 1.1720936. That's the beauty of Newton's method. I can numerically find these solutions, but the catch is I have to guess, give it an initial guess, and it's going to converge and typically find the solution close to my initial guess. That's problem 4. Problem 5 is exactly the same. If I have these two functions, back from homework set 1, this is y1, y2, here is y1, here's y2. There are actually 4 solutions. Off the graph, I can sort of get what they are. Using Newton's method, I can find them more exactly. Same procedure as before, just change my two y1s and two y2s. So you guess, my initial guess, perturb it slightly, find the next value, repeat 10 times. And my initial guess tells me which solution I find. If my initial guess is minus 3, I find the solution near minus 3. And that solution is actually minus 3.11525.101. If I initially guess minus 2, it iterates, and it's actually minus 1.626347172. Near 0, there's my third solution. If initial guess is plus 2, there's my fourth solution. So again, that's the beauty of Newton's method. I can solve for a function equals 0, and with that, I can solve two equations, two unknowns. Problem 6 is the little shoot game. So shoot isn't a valid MATLAB command. It's a M file we create in this class. If you go to Python Academy on week 2, you can click on it and download this code, copy and paste into MATLAB, and I pasted it under 111 homework 2 shoot. If I try to run it, I get an error message saying you can't run functions, but I can call it. If I go over here and say, let's call shoot, I'm going to shoot a tennis ball at 50 meters per second, 60-degree angle, and targets at 94 meters out. Do I hit the target? So that brings up a window that launches a tennis ball. Here's my target right there at 94, and I missed. My target is 40.4 meters short. Problem 6 is hit the target using trial and error. Just guess, guess again, guess again. So 50 meters per second was too fast. Let's try 40 meters per second. Okay, again, a little bit too far, so let's try 30 meters per second. You can guess, guess again, guess again. Guessing does work. There are better methods. One of those methods is Newton's method. With Newton's method, what I do is same as before. I give it my first guess. I'm going to launch the tennis ball at 50 meters per second. I'll then see where I hit, perturb it slightly, see where I hit, calculate the next guess. So that's based upon the previous two guesses. Draw a straight line to see where it hits the x-axis to where the answer should be 0 if it was linear. That's my next guess, display it, and repeat. So seeing how that works, there's my first guess. That's shooting at 50 meters per second. Does a second guess, perturbed by 0.01. From that, calculate x3. I'll then launch again. Closer. In MATLAB, you can see the error. First guess was long by 40 meters. Second guess, I was short by 6.7 meters. Here's my third guess, the third iteration. Just about dead on. That's Newton's method. Very quickly it converges. Kind of rule of thumb, if you ever see an algorithm with the word Gauss or Newton on it, it's probably a pretty good algorithm. Newton's method is a good way to find function equals 0. It's also referenced in the movie Hidden Numbers when Sheldon's talking about, wow, that's really archaic. It's not that archaic. We use it all the time. It's a really good way to solve function equals 0. So that's homework set number 2 for ECE 111. The point being, polar to rectangular conversions, you got sine and cosine. Anytime you want to plot in MATLAB, you need to plot xy. And solving function equals 0. Random guessing works. There are better methods. There's Newton's method, California method, interval halving. Newton's method is one of the better algorithms. Homework set 2 for ECE 111.